Hi, I'm Rachel Gehlhar, and today I'm going to present our work on data-driven characterization of human interaction for model-based control of powered prostheses, where we take motion capture data to estimate the interaction force between the human and the prosthesis, which we characterize with force tubes. We then use these to construct a model-dependent prosthesis controller, which we demonstrate in simulation. In the video on the right, you can see me walking with Ampro, a powered prosthesis at Caltech. The reason we study powered prostheses is because passive prostheses increase metabolic costs and hip power for amputees. Powered prostheses, on the other hand, provide net power to the user and enable healthier gait. Most current prosthesis controllers are model independent, meaning they do not account for the dynamics in their control method. This is because there is a human acting on the prosthesis and influencing its dynamics, but this human behavior is unknown, so the prosthesis dynamics are not fully known. Model-dependent prosthesis controllers can be constructed with the help of a force sensor. By measuring the force between the human and the prosthesis, which is at the socket for an amputee, the prosthesis then has full knowledge of its dynamics for model-dependent control. One problem with this is that force sensors are noisy, expensive, and not robust. This makes it difficult to implement these methods on hardware. Motivated by this, we develop a method to estimate interaction forces to construct a model-dependent prosthesis controller without a force sensor. I will give a brief introduction of our method and then go into more details about each component. We start by taking motion capture data of the human with the prosthesis to obtain joint trajectories, which we then play back in simulation with the human prosthesis model. In this simulation, we can calculate the socket interaction force. We do this over multiple steps and then characterize this range of forces with a tube. In parallel with this motion capture data, we do gait matching, where we develop a stable walking trajectory that is close to the motion capture data. This stable walking trajectory allows us to simulate continuous walking to test our controller. And this walking is then similar to the behavior of the human in the motion capture. So in our simulation, we have the human following these trajectories. The prosthesis is also following its original trajectories, but with a controller that guarantees stability for any force within this tube. We demonstrate these results in simulation. The powered prosthesis used for these experiments is called Ampro 3, and it has an iWalk adapter that allows an able-bodied subject to strap their knee to the device and do testing. It has two brushless DC motors to control the knee and to control the ankle. These motors have encoders to read the joint positions and velocities to give feedback to the controller. It is currently controlled by a robust passive controller. This has some model dependence, but it does not account for the interaction force. In our motion capture experiments, we place motion capture markers on the human and the prosthesis, and then the human walks with the prosthesis in a room with cameras surrounding it that track the motion of those markers. Now, we did not use a standard human marker model set for this since our system is asymmetric with the prosthesis. So instead, we put a number of markers on each segment of the limbs, and we registered these sets of markers on each limb as a rigid body in the tracking system. And then that tracking system gives us the limb pitch, and from these we can calculate the joint angles. We obtain joint trajectories from the recorded motion capture data, and then we play back these trajectories with a human prosthesis model. We construct this model as a bipedal robot with a series of rigid links and revolute joints. The human parameters are based on this user's height and weight and human data from these sources. The prosthesis parameters are based on Ampro 3. Now, while this is a rudimentary human model, as opposed to a more sophisticated musculoskeletal model, it suffices for our purposes to demonstrate the advantage of our control method, and it works well to integrate it with our model of the prosthesis. To estimate the socket interaction force, we model a fixed joint at the interface between the human and prosthesis with holonomic constraints. We use these constraints to calculate a constraint wrench to obtain the interaction forces and moment between the human and prosthesis. Then with data playback, we calculate the force profile for multiple steps and then fit a tube around the range of forces. With the motion capture data, we also develop stable walking gaits, shown here in blue, for the human prosthesis model that align closely with the motion capture joint trajectories, shown in black. We use optimization to minimize the difference between these trajectories and satisfy partial hybrid zero-dynamic constraints. These constraints guarantee stability in the presence of impacts and zero dynamics. By developing these stable walking trajectories, we now can simulate continuous walking similar to that seen in motion capture, so that we can replicate the behavior of the human to test our controller. We construct our prosthesis controller as a quadratic program, or QP. The cost contains model-dependent feedback linearization terms to track the stable trajectories similar to that seen in motion capture. So here's our QP, which is solving for our prosthesis control input, and it's minimizing over the feedback linearizing controller to track our desired trajectories. It is subject to these constraints, which I will now describe. We also use the model information in a control-Lyapunov function, or CLF, to guarantee stability for the system. This is shown in this simulation video where the prosthesis face portraits yield stable periodic orbits. This is for the knee and this is for the ankle. Our CLF stability is given as a constraint in our QP to be satisfied for any force within the tube. So this is our CLF condition, which is a function of the socket force. And this condition has to be satisfied for any force within this range, that range being these force tubes that we constructed. In conclusion, we constructed a model-dependent, robust CLF-QP to guarantee stability for any force within the range we measured through motion capture data playback. This controller outperforms the current robust passive controller and a PD controller in simulation. The robust passive controller used in the experiments had some model dependence, but it did not account for the interaction forces. And so in this simulation study, we had the human follow different gaits that were different from the nominal gait. So the prosthesis was receiving a force different than what it expected. But because our robust CLF-QP accounts for a whole range of forces, it was still able to achieve stability with this. We started the prosthesis at a perturbed initial condition, but the robust CLF-QP still converged quickly to the trajectory and converged more quickly than the other controllers. For future work, we are working on implementing this controller on hardware on AMPRO 3 to demonstrate the first model-dependent prosthesis controller that accounts for the interaction force. We could also use the force data from this work to develop a force sensor filter to reduce noise by providing a mean and covariance for a Kalman filter. So this would then allow us to have the force sensor be used as real-time feedback in a controller, because this could give us a way to reduce the noise, which is one of the biggest problems of implementing this controller on hardware. Thank you for your attention, and with that, I would like to acknowledge my co-authors Yuxiao Chen and Dr. Aaron Ames. This work is funded by the National Science Foundation, and here's my contact information. If you have any questions about this work, I'd love to hear from you and discuss it more. Thank you.